support vector classifier. All right, so we have this hyperplane, that we discussed earlier. We've got this unit vector of our coefficients equal to 1. Now we're in a situation where we may not have separable classes. We may not find m greater than, there may not be a solution, so we're going to have a little bit of a soft margin. And so we want to find a linear hyperplane that almost separates the classes, meaning that the margin can be violated by some of those training observations. So as I said before, we can't violate anything with the maximum margin hyperplane, but now we're in a situation where we can. We can violate whether it's within that margin, and we can even have observations on the other side of the margin, of the side of the hyperplane. So rather than seeking the largest possible margin so that the observation is not only on the correct side, we can allow, we're basically deciding that it may be worthwhile to misclassify a few training observations in order to do a better job at classifying the remaining ones. So it's like give up a little bit for a few so we can gain a lot for the majority idea. So how does that work? We've got these psi i's here. These John. So, we started out with our M, that was our maximum margin classifier, but now we have a little bit of something going on here, and these things are called slack variables. So they're the reason why this thing is called a soft margin, a support vector classifier. These slack margins, they tell us where the ith observation is located relative to the hyperplane and the margin, and they're the reason why we have a soft margin because the value psi I in this constraint here, it's proportional to the amount by which the prediction is on the wrong side of the margin. So if psi I is equal to 0, then the ith observation is on the correct side of the margin. If it's greater than 0, it's on the wrong side of the margin, and if it's greater than 1, here, it's on the wrong side of the hyperplane. So it kind of does a lot with allowing the wrong side of the margin here and the wrong side of the hyperplane. And so because, the psi i's are, the sum of the psi i's are bounded by this constant, and they're all greater than 0. So I'll talk about that constant a little bit more. Here, by bounding the sum on the constant, we bound the total proportional amount by which the predictions fall on the wrong side of the margin. So we actually have misclassification when the psi i's are greater than 1. So by bounding these psi i's, we can bound the total number of misclassifications by that constant as well. So that constant is actually called a tuning parameter. If we maybe I'll just call it C for now, and that tuning parameter C bounds the sums of psi i's and determines the number and severity of the violations to the margin and the hyperplane that we'll tolerate. So it's kind of like a budget for the amount that the margin can be violated. So if C is equal to 0, there's no violation. If it's greater than 0, then no more than C observations can be on the wrong side of the hyperplane. So once we have solved the optimization problem, we can classify a test observation by simply determining on which side of the hyperplane it exists. So that's what this sign is. And so how do we solve this problem? That's actually a convex optimization problem. So if some of you are taking computing or took computing, you know what I'm talking about. It involves quadratic programming with Lagrange multipliers, and I'm not going to get into all of that because it's beyond the scope of this talk, but if you're interested, you can read the elements of statistical learning and papers and stuff like that. But it definitely is an involved process to actually solve this problem. Okay, does anyone have any questions? If that makes sense, what I just said. First time giving this talk, so. All right. Okay, so here's an example of a support vector classifier. If we look at the left picture, we've got some purple observations. We've got, 3, 4, and 5 there on the right side of the margin. We've got 2 that's exactly on it. 1 is inside of the margin, and we've got these observations over here. This is inside. So we're not misclassifying anything, but we do have some things violating the margin. And over here, we've got, this is a misclassification. This is within the margin. This is a misclassification, and this is within the margin. So really the only 2 differences between these pictures are these 11 and 12. But this is what a support vector classifier allows. It allows these misclassifications, and it allows these observations to be on the inside of the margin, whereas if you remember the maximum margin classifier, this cannot happen at all. And that's what the psi-I's do for us. Okay, so I'm going to go over that tuning parameter a little bit. These are just some pictures of how the tuning parameter affects the margin. So the largest value of C, that tuning parameter is up here, and then C just decreases in this direction. So this is the largest one, this is the next smallest one, smallest. As you can see, that as you increase C, you increase the margin, and as you decrease it, the margin decreases. So what a bigger tuning parameter, or C, means is we're more tolerant of violations, so that's why that margin is larger. And as C decreases, we're less tolerant of violations. And so in practice, if you want to know how to figure out what C to use, you use cross-validation techniques. And so it's kind of a little bit of, you kind of have to play around with it to get the optimal one. And that's actually still an area that is, there's no one right way to figure out what C to do. You just kind of have to play around with it. So I'll talk about that a little bit later. But C controls the bias variance trade-off. So when C is large or small, we seek narrow margins here. And this amounts to a classifier that's highly fit to that data, but so that means it may have low bias but high variance. And on the other hand, when C is larger, up here we have a wider margin, and so that allows to fitting the data that's a less hard fit to that data, but the classifier that we get may have more bias, and even though the variance may be small, it may be actually more biased. So there's a little bit of a trade-off. It depends on what you're aiming to do. It's just good to know that even when you are choosing this C, you may be increasing your bias or you may be increasing your variance.